In this note, we'll discuss big idea number 1, talking about the rates of chemical reactions and how we describe them quantitatively. We will tackle learning target number 4. So by the end of the lesson, you should be able to determine the rate of a reaction experimentally and discuss appropriate lab strategies to use for a specific reaction. There are many ways to calculate and communicate how fast a reaction is going. Since reactions don't go at a consistent speed, they start off fast and slow down over time. Chemists often describe the average reaction rate. To calculate the rate, a specific chemical is chosen in the reaction and the amount that it changes is observed. Rates are always communicated in positive numbers, even if you have chemicals being consumed. Here are 3 methods to calculate the rate. The average rate equals the change in moles of a specific chemical divided by the change in time. This equation works really well if you have a solid reactant that you keep track of, or a solid product. If you have a gas or a solution, you might use this equation. The average rate equals the change in moles per liter divided by the change in time. Or you can also find the average rate graphically by taking the slope of a secant on a concentration time graph. Here is an example. On this graph, we have the concentration of a product being tracked over time in seconds. To calculate an average rate of reaction, I would take 2 points that I was interested in and draw a secant. Then I would find the slope of that line by taking the rise and dividing it by the run. Sometimes you'll need to calculate the instantaneous rate. You would do that by finding the slope of a tangent. An instantaneous rate is how fast is the reaction going at a particular point in time. You would draw a tangent line just grazing the curve and find the slope of that. You may run into this in later courses. If you are interested in a different chemical than the one that the rate is measured in, you can convert rates using mole ratios. Here's example 1. If I do a single displacement reaction between aluminum and barium chloride, this would be my balanced chemical equation. If the rate of aluminum being consumed is 10 moles per second, how could I find how fast barium is being produced? It doesn't get produced at the same amount because of the mole ratios in this balanced chemical equation. In order to convert this to rate of production of barium, I times by the mole ratio 3 bariums for every 2 aluminums. That gives me 15 moles of barium per second being made. Pause the video and try example B. The answer for example B, you can start with either the 10 moles per second of aluminum or the 15 moles per second of barium. It doesn't matter where you start. If I want to convert this into barium chloride, I use the ratio 3 over 2. That also gives me 15 moles per second of barium chloride. Now, I mentioned in order to determine the rate, you need to pick a chemical that you can keep track of. Well, how is this done? There are many ways to experimentally measure the amount of a chemical being consumed or produced. You must choose an appropriate method depending on which reaction you are working with and what equipment you have. Below are some commonly used strategies. Method number 1. tracking the mass. If your reaction produces a gas, the loss of mass can be observed in an open container on an electronic balance. You need an electronic balance to do this. You can't use a triple beam because by the time you measure what mass you have, it's already changed because you've lost more gas. You take the change in mass over a period of time and calculate the moles of gas made by using the equation mass equals moles times molar mass. The second method is by tracking pressure. If your reaction produces a gas, a pressure increase can be observed in a closed container with a pressure gauge on it. You would take the change in pressure and sub it into the ideal gas law to solve how many moles of gas was made in a particular amount of time. Method number 3 is by tracking volume. If your reaction produces a gas, it can be collected through a method called downward displacement of water, and its volume measured. You could then use the physical properties of the gas and plug it into PV equals nRT to find out how many moles of gas were produced in a particular amount of time. Downward displacement is an interesting technique, and this is what we're going to be using for our next lab. You're going to be doing your reaction in an Erlenmeyer flask, and your reaction will produce a gas. We'll do the reaction with a stopper on the flask with a tube inserted. Then you can collect the gas at the end of the tube. But most gases are clear and colorless. So how do you tell the volume? What you do is you take the end of your hose and put it in a container of water. Then your gas will bubble out. You collect the bubbles in a measuring instrument filled with water. As your bubbles come up, it will force the water in your test tube or your graduated cylinder down, and you will see one large bubble of gas, which then you can measure the volume of. Because the gas pushes the water down, this method is called downward displacement of water. Another way to track if chemicals are appearing or disappearing is by using a pH meter. Recording pH changes over time with a pH probe measures the consumption or production of an acid or a base. You can then find the molar concentration of hydronium, H3O+, by using this equation. pH equals the negative log of the hydronium ion concentration in moles per liter. We'll be using this equation more extensively in the next unit. The fifth way you could track rate is by using a voltmeter or an ammeter and looking at the changes in electrical conductivity. If the reactants and products have different quantities of dissolved ions, this will cause a change in the conductivity of your system over time. Sixth way is if you have one of your chemicals in the reaction has a distinctive color. You can use an instrument called a spectrophotometer to track the change in color intensity. There's a direct relationship between absorption of light due to color and chemical concentration. The higher the concentration is, the more light gets absorbed. Let's have a look at example 1. Which methods could you use to experimentally determine the rate of the reaction for this following equation? Look at the list of 6 methods and see which ones are possible. The answer to this example is in the next video.